I hired Aaron as the first Solidity programmer in Philadelphia. Let's say it that way. I paid him way too much because I paid him in Ether way back then. So how many of you here have cryptocurrency or are fairly familiar with cryptocurrency? How many would claim to be down the rabbit hole? Yeah, so everywhere I go, I talk to people and they're down the rabbit hole. And I am completely down the rabbit hole. My wife has me a bit on a diet and she's feeding me like all these carrots. So I think I'm like so far down the rabbit hole that I'm like becoming a rabbit. So, I'll just have our panelists introduce themselves and then we'll get into the discussion.
Should I start?
Sure.
Hey guys, great to meet everyone. My name's Rettig. Super brief background. I've been a software developer for my entire career. I have a background working in like quant finance on Wall Street for a few years, and then changed gears, came back to school here at Wharton, did an MBA, graduated 2014, so it's good to be back. Exciting. Any of you guys who are graduating soon, you should look at careers in blockchain because this is the good time to get into it. I became an entrepreneur, had a sort of healthcare technology company for a while, and then more recently, during some time off, I was doing a sabbatical. I kind of discovered Ethereum and went down the rabbit hole. We all have our version of that story. And I kind of occupy two distinct but related roles in the ecosystem today. So first of all, as a software developer, I think that stuff that's happening in the technology and especially the protocol layer today is super interesting. So I'm a core developer working on some of the low-level Ethereum virtual machine stuff. I also founded a nonprofit based in New York called Crypto NYC, and hopefully we're going to have a Crypto Philly soon as well. We're talking about it, which is kind of a space, like a safe space, and that's both a sort of digital space as well as a physical co-working space where people can come in and cut through the noise and get up to speed, and we act as a trusted resource. We have content, we have events every week, so everyone in the room, please, next time you're in New York, check out cryptonyc.org. We have events every week, and you're all welcome to check them out.
So my name is Mark White. In the pre-blockchain, prehistoric days, I was a principal architect at Expedia, but now I'm CTO of Media Protocol. We're creating a system that records URL interactions on the blockchain. And the idea is, on the one side, you've got users, like you or me. On the other side, there's a mixture of brands and publishers who've created content they want to promote. Right now, they're probably paying Google, Facebook, or other intermediaries to get that content out there. And then you've also got publishers who are creating content that they want to charge for. There's the New York Times of the world, Wall Street Journal, also Spotify, those sorts of organizations. And the idea is to create a frictionless ecosystem of the three so we can remove that friction of consuming the premium content, but also we can get rewarded for consuming promoted content and for sharing our data as we're doing those interactions and those are getting logged on the blockchain. We're actually able to get something back and have transparency over that, which is something that's sorely missing today. So, and shall I talk about with relation to scaling or okay.
Okay, so I'm Shin'ichiro Matsuo. I'm also originally cryptographer and a research scientist on the cryptography and applied cryptography area. I designed many cryptography protocols like eCash, e-voting, auctions, and so on. So in late 1998, 1999, I was engaged in the eCash systems by NTT and Bank of Japan. This is a smart card at the time. So this is open loop type of the eCash systems. So transferring money by using the data signatures. Unfortunately, it took 20 seconds to transfer money at that time. But this is the early stage of that eCash system before that Bitcoin blockchain. And I'm also a project leader at the ISO standard for blockchain distributed ledger technology for security technical specification. And I also initiated a new research center at the Georgetown University called the BTED Blockchain Technology and Ecosystem Design Research Center. And I'm also a co-founder of the bsafe.network. This is an international neutral research test network by international university. Currently, we have the 28 universities from all over the world. This is the same as the NSFNet and the BSD, which helped the development of the internet technology. And we are now reconstructing the same structure for the blockchain technology. Yeah.
So we're going to talk about scaling. Is my microphone working? We're going to talk about scaling today. We're going to start talking about what the problem looks like to the users of the system and why it's important that it gets solved. And then perhaps a little bit about why it's so difficult to solve the problem. And then we're going to try to look at some of the solutions that people are proposing for both Bitcoin and Ethereum. So I'll just start by asking Shinichiro, were you talking about scaling solutions back in 1999 when you were, because I have a feeling that people have been talking about this scaling problem since the beginning of the
Yeah, so in 1999 there was not blockchain technology. At that time that the problem was the cost for the data signature, calculating data signature scheme by using that kind of smart card chip. But this time, so they have that two major things for the scaling issue. The first is the P2P network. So for the public blockchain technology like Bitcoin and Ethereum, the number of that nodes, network nodes, relate to the security level of that public blockchain. So bigger number of that nodes can have that more security of that public blockchain. But when we have, for example, 10,000 internet nodes all over the world, we need to propagate each data to 10,000 nodes by using P2P network. And that time to propagate all data to the world takes time. And of course, when we establish a P2P network, we need to have that, for example, 500 seconds to initiate the P2P network. This is a lower bound to maintain that P2P network. This is the first thing. And the other thing is we need current Bitcoin blockchain have that 1 megabyte block size per 10 minutes. So this is a huge constraint on the throughput of the payment over Bitcoin network. That's fine. So if we would like to expand that block size to 1 gigabyte per 10 minutes, we can scale that the number of that transactions per second, 10 times than the current form. But in the public blockchain technology, all nodes should record that one block per 10 minutes, and this data is accumulated. So if we record that 1 gigabyte per 10 minutes, that kind of data is addition to each node. This implies that only the rich person, the rich organization can be that part of the Bitcoin blockchain network. And philosophically, it is not a fully decentralized network. This is also a problem of the current Bitcoin blockchain for the scaling issue.
And Mark, maybe you could speak about your experience with trying to use, I guess you're using the Ethereum blockchain?
That's right.
And how it's either getting in your way, the scaling problem.
I mean, it's huge for us. As I mentioned, we want to be recording every interaction with URL on the blockchain. That, if you think about having a decent number of users and how many URLs you kind of interact with a day, that's a lot of data. So to be able to truly implement the kind of protocol we're trying to build, when you look at Ethereum at the moment, it can handle in the region of 8 smart contract transactions a second. And that's across every single application across the entire world. Well, I think between this room we can browse more URLs than that very easily. So right now where Ethereum performance is at isn't sufficient to be able to build the kind of application we want to build. But at the same time, there's huge value to being able to build these kind of applications on the blockchain. So scaling the blockchain is really, really important to us. And so we're starting off initially with a model where we're using blockchain for settlement rather than recording all the data there. That just has to be a stepping stone because we're not gaining a lot of advantages of the blockchain unless that data is going somewhere that is verifiable, that is public, that doesn't need trust in a central node. And that's why this is just absolutely critical for us to be able to move forward.
So Shinichiro touched on this a bit late, but I'm just as a naive solution to the problem, if you have a 10-minute block time, why can't you just make a 5-minute block time and get twice as many transactions?
Yeah, it's a good question. So I mean, when we think about scaling blockchains, I think it's helpful to sort of understand that there are a lot of different initiatives and that there's sort of a taxonomy of these initiatives, which maybe we can circle back to later if it's interesting. But I think at the very sort of first level are certain naive solutions. I think that increasing the block size is one of those, right? So if you imagine, let's just talk about Bitcoin, because Bitcoin is the one most people are familiar with. It's a bit simpler. You think of sort of the Bitcoin blockchain as like a train. This is one of the visualizations I use, right? And it's moving a certain number of cars per second. And think of each car as one block, right? So one thing we could do is we could double the amount of stuff we put in each of those cars, right? That's effectively doubling the block size. Another thing we can do is we can shrink, well, I guess we could speed up the speed of the train, right? To your question about going from 10-minute blocks to 5-minute blocks. And to put things in context, Ethereum has 12-second block times. And so you definitely can make the blocks faster, but the reason Ethereum is able to do it where Bitcoin can't is because Ethereum has a different protocol, which introduces the concept of uncle blocks. So, okay, let me rewind slightly. So when you decrease the block time, so okay, I'm going to rewind even slightly more. I want to make sure everyone's on the same page here. This stuff is complicated. It gets complicated very quickly. So my blocks are produced through this process of mining. Okay, I think everyone has heard of that before. So what is mining exactly, right? So mining is like a cryptographic race, a computational race that kicks off. Every time a new block is produced and propagates throughout the network, all the miners receive that block, and that's their signal that that round of the race is over, and it's time to move on to the next round. And so they all begin running this very complex algorithm on their computer looking for basically a solution to a problem. And on average, because of the law of large numbers, it takes 10 minutes. It may take 1 minute to mine a block. It may take 60 minutes to mine a block. But on average, over long periods of time, it works out to 10 minutes in the case of Bitcoin. What can happen is, let's say that I'm a miner and I produce a block. And I broadcast that to the network. And Jay's a miner. And at roughly the same time, within the same second or 2 seconds, he produces a block as well. So we both solve the problem at roughly the same time. And we're actually separated not by 10 feet, but by 10,000 miles, right? So in the time it takes my block to reach him, or his block to reach me, we may have both produced a block and end up in a situation where those blocks conflict. Now, in the case of Bitcoin, that's not a problem. There's a mechanism in the protocol whereby that, there are situations where that could produce a fork, but in practice, that's very rare. And it sorts itself out, and one block, miners sort of know which block to pick, and over time, kind of, that doesn't become an issue. But the point is that the shorter the block interval, right? So if we go from 10 minutes to 5 minutes, the more of those collisions will happen. And so there's a limit to how far you can go. That's the short answer to the question. And so it reduces the sort of efficiency of mining and just makes it more expensive.
So you'd have less miners if you had larger blocks or something like that?
Potentially, yeah. And Ethereum combats this through the concept of uncle blocks. So the idea here is, if I produce a block and he produces a block, and let's say his block wins and ultimately gets added onto what's called the canonical chain, the sort of chain that wins, I actually still get a partial reward for producing my block, even though his block won. So that's one way to address that, and that allows us to bring the block time down substantially and not piss the miners off too much. But again, there's a limit to how far you can go.
So you mentioned a taxonomy, so do you want to begin that
All
conversation?
right, yeah, let's dive in. So I'll just walk through this.
May I just interrupt? I'm going to just let this get as technical as it wants to get, because I think a lot of the other panels are not so technical. So raise your hand if you really don't want technical, but rock and roll, here we go.
It's a technical panel. So here's what I'll do. I'll try to do this in like sort of 60 seconds or like 2 minutes or something. I just want to introduce the idea, and then we can drill down into, I want to hear from you guys what you think, obviously. But all right, so the simplest solutions are what I call kind of naive solutions. We were talking about this earlier. So this is things like increasing the block size. Another good example of this would be compressing data. In the Bitcoin world, there's things you can do like, you guys may have heard of segregated witness. That's kind of a version of that. Another example is batching transactions. It turns out that if, in Ethereum, if I want to send a transaction to you and you and you and you and you, I could make those as 5 or 6 individual transactions, or I could batch them together and route them through a smart contract. And by doing so, I can save gas. And these things are all low-hanging fruit, and they're all worth doing. But the important thing to recognize about them, there's very little cost. In fact, there's sort of no cost to some of these things. Obviously, the block size we talked about, there's limits there. But the point is, you get low factor improvements. You're not going to get orders of magnitude improvement. You might shave off 10, 20, 30%, or be able to squeeze 30% more transactions through the system. But we need to go from 7 to 10 transactions per second to sort of 10,000 transactions per second. So we need something better than that. So then the next thing we move up to is what are called kind of layer 1 scaling solutions. And layer 1 means it's on blockchain. It actually, on-chain is another word for this, and it involves actually changing the actual core code, the core consensus protocol kind of mechanism, that layer of change. And so that's a very difficult change to do. It requires coordinating a lot of parties together. And the big example of this today are things like, in Ethereum world, we have sharding, which that's a complex topic as well. But basically, instead of having every node validate every transaction you have, you do what's called sharding. So each node only watches a subset of transactions. That's the short version.
Is there on-chain solutions happening in the Bitcoin area, and what are they? What are they called? Layer 1 solutions. What would they be called?
Yeah, well,
Layer 1 solutions in Bitcoin. What are they?
Currently, so I think that you may have that. So several division of the Bitcoin, original Bitcoin, the Bitcoin Cash, Bitcoin something. This is originally, so on-chain scaling solution is increasing that block size, and Bitcoin Cash has a 2 megabyte block size per 10 minutes, and the current proposal that's on-chain scaling is that increasing the block size. And you talked about the segregated witness. This is some kind of tricky thing. This is a part of that. So layer 1 technology.
Yep.
So as I told that, so the core of that, so transferring something is data signatures. The data signature has a little bit size of the amount of data. For example, 24/8 bits or something, and this has some part of that block size, and we can pushing out to that out from the block to that, so that data signature data and that hash digit is inside the block size. We can increase the number of transactions per block. This is things happen in the segregated witness. This is a compression. You mean? That this is another type of scaling technologies in blockchain, on-chain.
One thing that I think is important to think about is performance versus scalability. So there are things that we can do that will increase performance a bit, but they don't really have a big roadmap in front of them. They don't let us go 10 times, 100 times, etc. And so yes, it's worth doing them. We can get more, make the network more efficient. They're not really the answer to this problem. We need to be getting 100 times. And so we need strategies that, come out, if you've got a motorway or a highway, you can add extra lanes to it, but at some point it just becomes, the cost of adding extra lanes becomes unfeasible.
I like that metaphor.
It's a good one. And so with a lot of these kind of solutions, they're just performance tricks. They're not really scalability solutions. And that's why kind of you talked about them as naive. The block size, it's not a scaling thing. We're not going to be, in a few years' time on this enormous block size. Or if we were, the whole system would just end up as a little centralized shadow of its former self. So I think that's a really important contrast.
So if we stay on the on-chain or layer 1 solutions, sharding is the only solution that's a layer 1 solution that has promise? Is that a reasonable thing to say or not?
I think in Ethereum today, sharding is, it's a big statement to say it's the only one that has promise, but it's the most promising one by far in terms of it's pretty much worked out. We pretty much know how to do it. It's more just a matter of getting there. So there's a roadmap that's that's evolved quite a bit, but it's pretty clear what that roadmap is today, and there's teams around the world that are working on it. So that is the solution that the Ethereum community consensus has kind of come around, that solution. That is kind of what's happening in Ethereum.
And Mark, that's what you mentioned about a 100-fold increase as opposed to a smaller increase.
I mean, yeah, sharding is huge. The idea, even at the most basic level, that this one application is using the same everything infrastructure as every other application is quite wasteful. Never mind being able to shard further down to user level.
Let's spend a few minutes.
I want to explain sharding because I think it's also.
I would say that, okay, so for not only for Bitcoin, so for public blockchain, there are new research on the consensus algorithms instead of the proof of work. For example, so algorithm provided by MIT Professor Silvio Micari. This is another types of research to improve the performance of the consensus algorithms. But this is still the fundamental research. And,
so I think actually it's a really important area because do you want to talk a bit more before about this trade-off of trust and and performance?
Yeah, of course. So there is some kind of trade-off, so relationship among that, so security, trust, and the performance. So even in that consensus algorithm.
Yeah. So the idea is that so Bitcoin or Ethereum is any node can join it. You have a huge number of nodes, and there's no trust at all required in any given one of the nodes. And that's relatively slow compared to, at the other end of the scale, you've got these private blockchains, which have a small number of nodes, maybe 10 or 20, which use different algorithms, which can perform much, much faster. But it's not as decentralized. You need a lot more trust in each node. So there is a trade-off there, and that is a further route to performance outside of.
I don't know the actual threshold. So what number is enough for the decentralization?
Is it 1 or is it 10,000 or is it?
I'll tell you, it's greater than 1 and it's less than 10,000.
Okay.
We don't know more than that, I think. Yeah.
So I'm sure everyone's starting to see why it's such a complicated, difficult issue to solve. So did we explain sharding a little bit, or do we want to, or does anybody want to hear sharding? What
You
is
guys want to
sharding?
hear that, or do you want to hear something
Rock
else?
and roll. Look at all these people.
All right, let me give you the short version of sharding. So the way that
Is there one?
I'm coming up with it on the fly, so bear with me. It's a complex topic. So the way that blockchains work today, by and large, and when I say blockchains, I mean kind of this Nakamoto consensus, this kind of Bitcoin, style blockchain, which Ethereum inherited as well, is that every node processes every transaction. You've probably heard this said again and again and again. Every node processes every transaction, right? And why is that the case? Well, that goes back to this question of security and trustlessness, right? If I transact with the bank or something, or if I send a transaction in Venmo or something, it's stored in some private database. I have no view into it, and I have to trust what the bank tells me. When the bank tells me I have $274 in the bank, I have no way to verify that. I just have to go by what the bank tells me, and if I go to the ATM and try to take out $200 and it says insufficient balance, there's nothing I can do about that. So the whole point of a blockchain, the beautiful thing about Bitcoin and about Ethereum, is that you as a participant in this network, as someone transacting in this network, see every single transaction that flows through the network, and you can verify for yourself every transaction that this account has this amount of money, that there's no double spending happening, that kind of thing. That's the basic idea. Now that gives us that there's a lot of power in that, right? That allows us to build all these trustless, amazing apps and things on top of it. But the problem there is that we have a bottleneck. If you think about it, the entire network will never be faster than the slowest node in the entire network, because every node has to process every transaction. That's just reality. That's the way things work today. So the idea of sharding is asking this question: can we upgrade the protocol in such a way that instead of every node having to process every transaction, right? We do what's called sharding the network, and when you could have an arbitrary number of shards, you can have 10 or 100. I think for Ethereum, we've settled on something like 40 or 60, I think, as an initial number, although it can scale much higher in the future. And you only have to process then 1 out of every 40 transactions, or 1 out of every 100 transactions. That's the high-level idea. Now, getting that to work in practice is quite hard. But the beautiful thing about shards is you can then have shards inside of shards. and that's called quadratic sharding. So there's actually, theoretically, no limit to how much you can scale with sharding, which is one reason this solution is so exciting.
Are you trading off trust? Are you getting less trust
Yeah.
on the sharding?
So let's say that you have 1,000, okay, so we call them validators in the sharding world, and the terminology is also evolving slightly. But so today we have what are called miners, right? And miners are the sort of the people who, miners and actually for that matter, anyone, any full node, any node participating in the network today who validates every single transaction, they're contributing to the trust of the network. So yes, the answer to your question is yes. If you shard it into 40 shards, then each shard would by definition have 1/40th, give or take, the security of the whole network. But so there's a couple of ideas here. One is that maybe we have enough validators participating in the network today that that's okay, we have enough per shard. And two, with sharding, we move from proof of work to something called proof of stake, which makes it much easier for someone to become a validator. You don't need expensive mining equipment like you do today.
I'm just going to say, I think he said something like, with luck, we'll do that or something. So that's a big concern with something like that. But we only have about 10 minutes more left, and then we'll have some questions. So I wanted to move to now layer 2, and maybe we can explain what layer 2 means first. Would you like to handle that question?
Yeah. Okay. So to talk about the layer 2 technology, so we assume that the original Bitcoin or Ethereum blockchain is treated as a layer 1. The layer 2 is also using the layer 1 technology as it is, but so we need to have another logic or another program to input the layer 1 blockchain. But so, for example, the good example is the Lightning Network for the Bitcoin blockchain. Lightning Network is an additional payment channel to conduct a payment among our users of the Lightning Network. But so in the original Bitcoin, all payment information is recorded into the Bitcoin blockchain. But in the Lightning Network, so when we treat as some amount of the collection of the some amount of the transaction, then so the abstract of that the transaction is recorded to that original Bitcoin blockchain. This is the reason why so we can eliminate the size of the data recorded to the original Bitcoin blockchain, and we can scale the number of transactions per block. So this is the original idea to the layer 2 technologies. So I would like to addition that there are many kinds of layer 2 technology, not only for the scaling or performance issues. So for example, Tumbleweed or another kind of techniques to enhance both performance and the privacy. So the layer 2 technology is a collection of the technology to enhance performance, privacy, or other nature with using the original Bitcoin or Ethereum blockchain. This is the explanation of that layer 2 technology.
And Mark, do these layer 2 solutions solve any of the problems that you mentioned earlier about data size or data usage?
I mean, yeah, I think the layer 2 solutions look really, really promising. I mean, I'm following Plasma quite closely, which I'm sure you can explain in a second, but is a solution being worked on by Ethereum. That's another layer 2 technology. But the idea of moving a whole bunch of this stuff off of the core blockchain just has enormous promise to.
Do we trade off trust again? So
Yeah.
as we scale, we trade trust. Is that what we're concluding? It's not that simple.
No, well, so I think there's, I mean, maybe this is kind of a hot topic at the moment, like is to make something like Plasma work and be trustworthy, there's a huge number of engineering challenges or challenges of getting all of the incentives just right so they're balanced. So it's not worth doing something that breaks the committing double transactions or anything like that. And that's quite an area of intensive work at the moment.
Yeah, I would say scaling is probably the #1 area of kind of focused research work, definitely in Ethereum and probably in Bitcoin as well today. Yeah, on this trust topic, I would just add, I think the best and most promising layer 2 technologies, like Plasma is a good example. Plasma is an example of something called a side chain. We also have these things called state channels, which Professor Matsuo mentioned a moment ago. The best ones and the most promising ones do not reduce trust at all. This is the key thing, and they do that through various complex sort of crypto-economic incentive schemes, but the idea is you have the underlying blockchain itself, sort of the Ethereum main public chain in the Ethereum world, as an anchor of trust. And you can, like in a worst case scenario, like you can go off and do things off-chain and do them in a very efficient way, but you always have the option of falling back to the main chain, and things are going to be more slower and more expensive in that case, but you still have that level of trust. So you never lose trust with these solutions.
And at this time, original, I think that the first related technology was the Lightning Network, and this was invented in 2015, I think. And for Ethereum, so Lightning and Plasma as a layer 2 technology. And we can, so even if we can believe that so layer 1 technology is fully decentralized, but so there's no confidence about so Lightning is fully decentralized. There's some research on that. So the Lightning Network has a single point of failure in this payment channel. But the security of the Lightning Network and the security of the combination of Lightning Network and the Bitcoin is understudied. And so there are many researches is currently done. And so we need more time to figure out so what kind of trade-off is inside the layer 2 technology. And currently, so my project, BCF Network, is doing the layer 2 technology open competition to evaluate the technology of the layer 2 technology. I'm gathering that so any application on the layer 2 technology and its evaluation technologies from all over the world, and we are evaluating that kind of technology by using resources of the neutral academia. And so that kind of trade-off in the layer 2 technology is currently studied.
We have about 15 minutes. I want to leave 10 minutes for questions from the audience, so I'll just ask one more question. So this is difficult to really even ask, but I'll try. We talked about trust and confidence and making a change to a $20 billion piece of software deep inside of it. And does scaling include bringing along a whole population of people that trust you as the developers to make those changes? And what happens when that just disappears because people lose trust or people lose confidence? Is that part of the scaling equation, I guess? Is that a question that can be answered? Maybe not.
Hard question to ask, harder question to answer.
Yeah.
Who wants to take a crack at this one?
I think you guys have been, Ethereum's been very strong at kind of at doing this, having an upgrade cadence, at bringing their whole community with them on, okay, we've got this release now, and in this many months we're moving to this release, and this many months to this release. Every one of those is a hard fork. Every one of those, in theory, the community could decide, you know what, we're not cooperating with that, we're going to stick with the old one. And those are the huge challenges that Bitcoin has seen, in that it's not been able to engender that trust in its community, to be able to kind of say, this is the roadmap, everyone come with us on this, and not have a whole bunch of people go off on their own hard fork, as we saw with Bitcoin Cash. So, I mean, it's like, I think that is a political thing that Ethereum Foundation has managed very well politically.
There's always room for improvement. I think this is an excellent question. I think there are a lot of technical aspects to this question, but what's so interesting about it is it touches upon the philosophical, political kind of governance side of things. And personally speaking, I find the governance side of things as interesting, if not more interesting, than the technology side of things. It's actually something that I'm focusing on right now in terms of some of the research I'm doing. I mean, let's be honest, we don't have time to do justice to the answer to this question. This is hopefully the beginning of a conversation, but I guess my one sentence thought here would be that this is really at the heart of everything, this whole experiment, right? Why are we all here today? Why are we working on this technology? What's the freaking point of Bitcoin and Ethereum and blockchain, right? It is about trust, and it's about a new vision for, a way to build networks and systems by which human beings can transact with one another and hopefully do other things to build social networks and governments and things on top of them. And this is the big question, is how do we govern them, and how do we do a better job than we've done in the kind of existing nation-state system? And the cool thing is everyone has a veto, right? Because if you as a developer don't agree with a proposal, you don't have to implement it. If the developers implement it and you as a user don't agree with it, you don't have to run the software. So there's always this ability to exit peacefully. And that's the thing that blockchain has that nation states don't have.
Well, let's have a round of applause for the panelists. Questions, as many as you'd like, as much time we have here.
I have a question for you, Lane. My name's Eric Marks. So in a sharding scheme for Ethereum, how would you manage so say you have your 40th or your 30th or whatever, how do you determine which transactions are managed by that shard?
Okay,
is that by account? Or?
Yeah, let me preface this by saying that this is still in flux, and as I said, I think we're just at an inflection point today where it's becoming pretty clear. We've been through many versions of sharding, and if you're inclined, you should check out we have a number of resources. We have GitHub, I think it's github.com/ethereum/sharding. There's a lot of resources there. There's also the ETH Research discourse forum where this has all been coming together. So so we shard by accounts. So each account can either be what we call an externally owned account, which is just me having Ether in my own wallet, or it could be a contract, right? Lives on a particular shard. Mm-hmm. And whether or not you're able to choose which shard you live on is a bit of an area of research. And my personal belief is that you shouldn't be able to choose. It should be randomized, because if you can choose, then you'll just have a bunch of people clustering together. There'll be popular applications. Like, let's say the Aragon app is very popular, and so people want to be able to transact with Aragon, so everyone wants to be in the Aragon shard or something like that. Mm-hmm. So let's say that you somehow kind of figure out randomly. Like, randomness is really important in sharding. It's not important just for where the accounts are. It's also important for where the validators validate, because if validators are not attached to shards randomly, then it's much easier to mount an attack against one particular shard with a very small piece of the compute power in the network. Does that kind of answer your question?
Yeah, just quick follow-up. So would you ever, and this might if this gets too much into it, feel free to not answer, but would you ever consider like changing those accounts, like at some interval, like regenerate, basically draw the numbers out of a hat again, so that like shuffle which accounts are tied to which shard?
It's a good question. So the validators get shuffled across shards regularly. I think shuffling accounts would be a lot harder because there's state associated with accounts.
Right.
And that's a very difficult kind of data management problem. It's a good question. You should take that to ETH Research and we could talk about it there.
Ben.
So following up on that question then, if in a post-sharding world, if I'm running a node, do I still validate each block, or I'm a little bit confused. So you said accounts live on different shards, but how does the actual validation of blocks by nodes?
Right, so the first thing to know is they're not called blocks anymore. So all the terminology, it really is like, it's a rabbit hole. It's a rabbit hole inside of a rabbit hole, because it's like, we have these concepts of blocks and miners and block headers and all these things, and it's a completely different set of terminology, which also is evolving, and it's kind of a moving target. But yeah, so collation is sort of the word that we're working with right now, and I think that there's a reason specific words have been chosen here, because it's just a bit of a different idea. Another thing that Vitalik's been talking about recently is that contracts will not be called contracts anymore. What was the word he used? I think entities or something like that, because we're sort of generalizing the idea of there's a lot of abstraction going on here. I don't want to go too deep into this. I'm sorry, I've completely lost my train of thought. What was your question?
Well, it was that do nodes validate each block in post-sharding?
So yes, I mean the short answer is yes. So a validator would validate each collation in the shard that they're responsible for validating at a given point in time, but then that gets shuffled. So you'd have to validate a bit over here, a bit over there, that kind of thing.
I guess what I'm struggling with is so I have a very clear mental model of how the blockchain currently works. You have the block, you can perform the hash, you can make sure it's valid, you can make sure the hash points to the previous block. So if you are not doing that for each block, but only for some subset of blocks as a validator, how do you recognize that you have a valid block?
Yeah, it's a great question, and I mean, okay, so I'll try to answer this in 10 seconds, and I think this is also like, let's follow up on like ETH Research on GitHub or Gitter or something. We have a very active Gitter channel as well. If you guys know gitter.im, it's attached to GitHub to talk about some of this stuff. You get a heads up before you're assigned a shard, and that gives you a chance to download all the block headers for that shard. And so yes, there's still some sort of concept of a full node or an archival node or someone who has to maintain all the block headers for all of history or collation headers for all of the shards. And you'd have to download them to get caught up and get in sync. And there's various ways to speed that up. And then it's the same process that you're describing. It's just there's this preparation kind of phase, and then you do that, and then you get switched to another shard later.
In the back there?
Can we talk a little bit about the technical challenges associated with proof of stake and how Casper is doing to address?
Nate?
Oh, no, okay, proof of stake and Casper. Technical challenges, wow. I mean, it's a hard question to answer because proof of stake is really, really new. There are a number of kind of blockchains that are up and running using proof of stake today, but they're very different types of proof of stake. And so, okay, I guess the short answer to this question is the answer is usually in blockchain world, we have either dilemmas or trilemmas. We have sort of situations where you have to optimize for some set of things, and in optimizing for A, you're kind of, you can't optimize for B at the same time. And so in the case of proof of stake, you have things like the number of validators. Right, the more of them you have, the more security you have, but then the more of them you have, the higher the latency time and the more messages that need to get exchanged across the network, and that kind of slows everything down. It slows the block time down. Yeah, that's the biggest challenge in proof of stake. As well as just how do we get there? How do we transition from proof of work to proof of stake is a big question.
I just had a discussion when you were talking about about the shards only doing partial works, but you said there was an option of falling back on the main blockchain. So how would that transition kind of work?
So I think that's related to the plasma rather than the shard.
Well, it's true. It's true of all of these solutions. In the case of sharding, you still have a main chain. You still have a main Ethereum blockchain. That's not going away. And all of the we snapshot. It's the same idea applies for sharding and plasma and state channels and everything else. Basically, you take a snapshot of the data every so often, every number of blocks. In the case of sharding, we refer to these things called epochs, which could be 50 blocks or 100 blocks. You take a snapshot and you store that in the main Ethereum blockchain. So you can always go back to that as a root of trust. Does that make sense?
Kind of archiving it.
Sort of, yeah.
Maybe 2 or 3 more questions over here.
Hey, so yeah, I do occasionally hear arguments that proof of stake is untested, but there have been several, coins around now for 4 or 5 years that use proof of stake. Are you aware of any proof of stake consensus failures, or just is there not enough value in those coins yet? What's the worry, I guess?
I would argue that the networks that are up and running using proof of stake, it's a different type of proof of stake. The most common version of it is called delegated proof of stake, or DPoS.
Yeah.
So there's many of these networks. You probably heard of things like EOS and NEO. Lisk is one that people mention a lot that has been up and running for a few years. They're pretty centralized. So I don't think, and feel free anyone in this room to challenge me or correct me if I'm wrong, I don't think anyone has done proof of stake anywhere near the scale that Ethereum is planning. We're planning thousands or tens of thousands of validators. No one's gotten close to that. A lot of these have, Lisk has this concept of super nodes or super validators, and there's tens of them, not tens of thousands of them.
And I would like to add that my concern is the condition of the operation. So for the proof of work, so from original Satoshi Nakamoto assumed that all nodes is the same capability of the calculation. But the reality is that there's so many mining pools, and so most of the mining power is in the China behind the Great Firewall. This is the reality. So we need to consider about the condition of the operation. My understanding is so we need to more study on the condition of the operation for proof of stakes.
I would say it's also very different to say, even, and I agree, the chains out there that I'm aware of are DPoS, but the incentives to find a flaw or whatever, when you're talking about Ethereum versus one of these small blockchains, the amount of scrutiny, and also the fact we're talking about a few years here, but we're hopefully building something that's going to be lasting a very long time. It's just dramatically different, I would say. So I wouldn't use the fact that nothing had been found on relatively small networks as it's not proof of anything. It's maybe evidence, but I think it's fairly weak.
I guess one more question, and then we'll wrap up. Good.
I'm interested to hear your thoughts pertaining to mostly any scaling solution on Ethereum. It doesn't seem like many people, although they understand the trade-offs, are talking about precisely how large the trade-off between scaling and attack cost is. So when you shard or implement plasma chains, you're always going to have less, at least a little less power concentrated on those solutions. So you definitely now risk attacks with much lower barriers of entry.
Yeah, so let's talk about plasma as an example here, because plasma is really interesting. So what I sort of postulated before is that for all these level 2, layer 2 scaling solutions, they're still anchored in sort of the public chain as a root of trust. And so like to the extent that you believe that Ethereum main public chain is trustworthy, then that trust would extend to sort of any kind of plasma side chain. So in the case of plasma is very centralized, right? Each plasma, I don't have time to explain exactly how plasma works, but you have to take my word for it. It's kind of another chain, right? Another blockchain that's kind of doing its thing, like a layer above the main Ethereum blockchain. And you have what's called a plasma operator. You have a single entity. It could be multiple, but we kind of start with a single entity who literally is responsible for like managing that chain and managing the blocks on that chain. And that sounds like super dodgy, right? Because like, what happens if that plasma operator, becomes evil or starts acting maliciously? There's a ton of very good quality videos on YouTube put up by Carl and some other people on the Ethereum team who will explain this really, really well. Well, the beauty of plasma is anyone can